So extrema, of course, and we're talking about absolute extrema. So the minimum or maximum value of a function, and then we'll get into mean value theorem. And a lot of theory here, and like I said, I think it's pretty cool when you really get down to the small view of a particular situation, but the big concept that it is involved in this. All right, so just to be clear, the extrema are minimum or maximum values. They're the y values, okay? Oftentimes, a mistake will be made because we start talking about the x values. That's where a minimum or maximum occurs. But the minimum or maximum value of a function is based strictly off the y or the f of x or the g of x or whatever the name is, okay? So we're going to be looking for those. Sometimes it's called global extrema. Sometimes it's called absolute extrema. So this notation, or this verbiage, I should say, global or absolute mean the same thing. Okay, they are greater than or equal to or less than or equal to all other y values possible of the function. The biggest or smallest possible y values of the function. It can occur more than once. That's why it's the or equal to. So let's say the maximum value is 50. You could have 50 occur multiple times. It's still just the maximum value. So that's why it's the or equal to part. Where we get a little blurry is when we talk about relative extrema. Sometimes that's called local extrema. Okay. Same idea. In a particular neighborhood, that phrase gets used a lot when we talk about relative extrema or local extrema. In this particular window that we're looking at, this particular neighborhood that we're looking at, we could say that this is the highest possible value or lowest possible value for that particular neighborhood, for that window. But it might not be a minimum or maximum for the whole thing if you pulled all the way out and looked at the entire function. Again, usually they're going to give you the window of the neighborhood. Okay. And so how this connects to derivatives like we've been working on is that the x values, where the minimum or maximum values occur, those x values, critical numbers or critical values, sometimes we'll say values here instead. They're the same thing. The critical values are the x, okay? And those extrema will happen, first of all, f of x has to exist at that value, and the derivative at that value is either 0 or undefined. So it's going to be important to know where you get the critical numbers from, because that's where the extrema are going to occur. And once we take the derivative, and you'll see, we'll go through this in a minute. Once you take the derivative, you just set it equal to 0 or figure out where it can be undefined, and then that's where the critical values, the critical numbers have to be. And those are the places where the extrema can live. All right. And we'll get into more of why that works as we move forward. The last thing, absolute extrema can occur at critical numbers or endpoints. This is a key point. If they restrict your domain, you have to test the endpoints, because the extrema can also occur there. And those endpoints do not necessarily have a derivative value of 0 or undefined. We talk about this when it comes to a continuous, ongoing, unlimited function. But if we chop off the graph because we restrict the domain, or because the domain is restricted, we could end up getting absolute extrema there too. Okay. So what's really important is recognizing as you're entering into problems like this, when they ask you to find the minimum or maximum, is the domain restricted or not? Because if it is, then you have a little extra work in terms of determining whether or not the minimum or maximum could occur at an endpoint. That's the takeaway there, okay? That's for absolute extrema. Relative extrema or local extrema can only occur at the critical values, the critical numbers, right? We don't have to worry about the endpoints when we talk about relative or local extrema. So these are all the rules, right? The conditions that need to be met, the things you have to think about before sort of getting into these problems, okay? Okay, moving on. All right, this is on page 86 in your book. And I want you to you can take a picture of the screen if you want, or you can screenshot it from your book if you want, whichever. And I want you to go through and try these first 6 problems. And then we'll discuss and see what you come up with. There's some funky stuff going on here, but one thing to notice is that it's not an unlimited function. The domain has been restricted for this particular case. All right, Andrew, what do you think? Absolute maximum of f?
Y equals 4.
Y equals 4. And that's going to occur right here at this point, right? I actually just wrote 4. I didn't even write the y equals. Okay. At what x value does f have an absolute maximum? Jackson? X equals negative 4. So now we're talking about what the x value is here. Easy enough. Now why I wrote x that time and I didn't write it the first, y equals 4 the first time, I don't know, to be honest. It's a good question. All right, absolute maximum point. So now I'll take this one. So now we're just saying put it together. Okay, negative 4, 4. All right, absolute minimum of f. Andrew, what'd you say?
I said it doesn't exist.
Why?
Because it's, f of x doesn't exist at the, endpoint there. Where it would be the smallest.
Yeah, see, so right. I mean, it should be here, yeah? But there's it's an open circle. So that means it's not negative 2. It's really, really close to negative 2. But of course, if you pick a number really close to negative 2, somebody else can pick another number closer. And we could keep having that game and get a number closer and closer and closer, and then we would die eventually because you could do that for an infinite number of times. So in this case, there is no absolute minimum of f, okay? And so that's the point we're talking about, so there is no one. Okay, so then we switch over to relative minimum and relative maximum, all right? So now we start looking at those windows. And in this case, they didn't necessarily create the windows for you. So you have to look at spots, if you created your own windows, your own neighborhoods, where there would be minimums. So Jackson, where do you see relative minimums for x?
At -3.
Negative 3. So this point here, right?
-1.
Negative 1.
Yeah.
Here?
1.
1. Okay. 1. Anywhere else?
Can you count the one that doesn't have a square touch for relative or no?
No, but what about this value? Doesn't this one count? Could I say that one? I don't know. Let's you know what I mean? That's the debate. Do we count that? The answer is yes. Okay, so again, when we think about minimum, relative minimum, or relative maximum, I know we get used to looking at the graph and going, oh, where are bottom points, so to speak. But the minimum and maximum are really just a value of the function. So even though in this particular case here, the function doesn't dip to it, the value still has the function still has a value at x equals 2, and it is relatively small, comparatively speaking. If I looked at this window, no, wrong one. If this is the window we decide to use, right? Relative minimum right there. Okay, comparatively speaking, that's the thing that's tricky about it. Let's see if I can make this all go back to what it was. Yeah, there we go. So, it's asking for the x values, so -3, 1. Okay. How about maximum, Andrew?
I said only -1.
Yep. It can't, because normally we would look at this graph and go, oh, up here. Well, we already established that when x equals 2, it's actually a relative minimum because of this open circle. So that's the debate, right? Is there one here? And the answer is no, there is not. Only at -1 because of this whole situation, open circle. It can't be here. But this is where we would normally look for them, right? The sort of peaks of the graph. But because this is an open circle, we can't count x equals 2. And again, you can't have a relative minimum and maximum at the same spot. Not possible. All right, easy enough, right? All right. Next, we're going to keep working with the extrema. All right, so this is number 9 in your book. Okay. Find the extrema of f of x at 3 times x to the 2/3 minus 2x on the closed interval -1, 3. So we don't have a graph. So in order to find the extrema, where do we need to look? The derivative, which will help us find the what? The critical numbers, the critical values. We got to find those. And what else do we have to do here? Besides finding the critical values, what else do we have to do?
Use the given interval.
Yeah, use these endpoints because the minimum or maximum could occur at -1 or 3 as well. And you can pretty much bet that the critical values are not going to occur at these two endpoints. They're going to occur somewhere else. So go ahead and give that a shot. Here's the derivative. Of course, that's what we have to do. We have to take the first derivative. All right, so the first derivative, 2 to the x, 2 times x to the -1/3 minus 2. Did you get that?
Yeah.
Okay. So then in order to find the critical numbers, we just set that equal to 0. And also consider where it might be undefined. Right? Those are the two places that you have to look for, because if it's undefined, there's a vertical tangent there. Right? And so we can have change there. So just the whole thing equal to 0. Now notice what I did. I made it a little more manageable. Let's throw this thing at the bottom. In order for all of this to be 0, what does this have to be on the bottom? 2, like what minus 2 gives me 0? What does this whole value have to be?
2.
It has to be 2, which means this on the bottom has to be 1. Okay? Which means x has to equal 1. All right, now I went through and solved it and flipped it and I did all the algebra. But long story short, this bottom has to be 1 in order for this to work. So x has to be 1. So there's one critical number. Say the question again. Is it undefined at 0, right? So if x was 0, would this be undefined? And yeah, the answer is yes. So I have to consider those two. Those are the two critical numbers. Okay, so I have a critical number at 1, and then again you have to consider that undefined case. So there's going to be 1 at 0. The only other thing that we have to keep in mind, so we're gonna test the value of f at 1 and f at 0. We just can't forget about the endpoints. So we actually have 4 numbers that we have to test. And these are not critical numbers, but absolute extrema can occur at the endpoints. So essentially what I have to do is I have to test 4 of these. F of -1, and I put them in order. I went smallest to biggest. You don't have to, it doesn't matter. So there's an endpoint, there's an endpoint. Plus they're endpoints, so I like to think of them as bookends. then I'm going to test 0, 1, and 3. So my question to you is that what you did? Yeah.
On 0.
You forgot about 0? Okay.
I did say.
Okay. So remember those critical numbers. Always don't forget about those undefined values. All right. And so of course we can go through and you do the algebra, and I'm gonna spare you all that time, but it's all just plug and chug. Right? So here's what it would look like. F of negative 1 is 5, f of 0 is 0, f of 1 is 1, and f of 3 is approximately 0.240. Remember, when you're rounding, always 3 decimal places, always, always, always. I don't remember if I rounded or truncated or if they're equal, I don't remember. But now, once we have the values, we can make the determination. All right, where is an absolute minimum? Which one of these is the smallest? 0. So that means I have a minimum occurring at 0, x equals 0, y equals 0. And my maximum value is 5, occurring at negative 1. So I went ahead and wrote them out. Okay, the maximum of f of x is 5, the minimum of f of x is 0. You could also write those as points, but usually when they ask for extrema, they're asking for the minimum or maximum value. If they wanted you to also say where they occur, you could restate that, but it occurs at negative 1. It occurs when x equals negative 1 and when x equals 0. Okay. One of the things I know for sure is that if you ever saw something like this on the AP exam, you would still have to show all of these values for the critical numbers and the endpoints. That would guarantee you all the points that possible on that FRQ, because you would be able to definitively say, look, this is the biggest number, this is the smallest number, and I tested these other numbers too, okay? And sort of prove that it's not there. All right, questions on that? That's all Extrema stuff. The mean value theorem, like I said, this is something where I don't know how well you understand the concept of this, but I really like this theorem because there's something really, in my opinion, pretty cool about it. And I like to relate it back to algebra. And, you know, we were talking in my Algebra 2 class in the last week or so, talking about slope and how slope is so big in calculus. And it's a simple concept, but when we start tying things together, I think it's pretty cool. All right, this is from your AB book, okay? I like the way they express it. So if you want to put this, you can either screenshot it from your AB book or you can take a picture of the screen here. But I definitely want you to have this the way it's written, because I think it is as clear as it possibly can be conceptually. The mean value theorem, there's a couple things you have to keep in mind. You have to establish continuity. You have to establish differentiability. Those are conditions that you must state. You can't just jump to the mean value theorem. And I know a lot of places you'll see it MVT. I'm not a big fan of that either. My preference is that you actually would write it out by mean value, using mean value theorem, by mean value theorem, something like that. So you have to state that f is continuous on the interval and is differentiable on the interval. Okay. Once you say that, and of course one's closed, one's open. Here's what it's saying. There's some interval AB. There's another number inside of that interval somewhere, such that the slope of AB is also equal to the derivative of that value C. So in other words, the slope at point C will have the same slope as the slope of a line segment AB. Okay, now here's, and then they just rearrange it. That's another way to put it. This is like point slope form. Here's the takeaway that I think you really need to understand. The slope at a point is the tangent line, the slope of the tangent line. That's what this is saying. At this point C, here's the slope of the tangent line. This is also often called the instantaneous rate of change. Okay? The slope of the tangent line is the slope at that exact moment. What they're saying is at some value C, that slope of the tangent line is going to be equal to the slope of the secant line, the line segment that connects A to B. And that's the average rate of change. This is the algebra version. This is slope. This is y1 minus y2 over or y2 minus y1 over x2 minus x1. This is the algebra version of slope. And what we're saying, there's some point C in this interval where the slope of the tangent line equals the slope of the secant line. And I know you're not used to talking about the secant line, I don't think. And I'm going to show you an example of what that looks like. Okay? And all this is saying. Okay? The mean value theorem states that given the right conditions of continuity differentiability, you gotta state that. There's at least one tangent line where x equals c that's parallel to the secant line, because that means they have the same slope. That's the big concept here. And I'm going to give you a visual that represents that so you can see it. And to me, that's the cool thing about the mean value theorem. Again, to me, this is the cool thing about it. That there's a point in this interval where some point in the interval somewhere where the slope at x equals c will be the same as if I connected A to B. Or it would really be A comma f of A to B comma f of B, right? To these 2 points, the point that occurs at A, the point that occurs at B. And so one of them is inside the curve, this one, that's the secant line. One of them is outside of the curve, that's the tangent line. And at some point in that interval, there will be parallel lines, okay? So let me show you, let me walk you through what it might look like visually, okay? So let's just, this is in the book. It's some general thing. And if you look in the book, you don't see the step-by-step. You see it already all written out. Okay, so here's some example. Okay, here's some curve. This is the point A comma f of A. So some point that occurs where x is A, some point that occurs at when x is B, B f of B. And what we're saying here is that there's going to be some point C in here where there's going to be a tangent line that will be parallel to the secant line. The secant line, okay, so here's the secant inside. I just connect the points. Inside the curve, that's called the secant line. The tangent line is always outside of the curve. So somewhere there is a C somewhere in here where I can draw a tangent line that is parallel to this line. And that's basically what the mean value theorem says. Okay, so the tangent line, so these 2 lines are parallel. The tangent line is outside the graph. And so we can see right around here, there's some value, whatever that is, where x equals c. So this is where we take algebra and connect it to calculus. And all we're talking about is the slope. There's a guarantee, the mean value theorem guarantees that if we have a continuous function that is also differentiable, that there's some place where the baby slope equals the calculus slope, which is the first derivative. And that's the whole concept. And that's why I think this is kind of cool. Okay? All right, I think we're doing one example. Are there questions about that? Does that kind of solidify your understanding of the mean value theorem? Good. So here's the one we're going to do. This is example 20. And this is a definite AP exam type of question. Now, for BC, it probably wouldn't be a standalone thing. It would be embedded in something else. But this is something you're going to need to know how to do. We're trying to find any C values. So notice it says all C. It's possible that there's more than one value inside the interval where the average rate of change will also equal the instantaneous rate of change. In other words, the first derivative will also equal the algebra slope. Okay. So we're going to have two things that we're going to have to find here. We're going to have to find the first derivative. We're going to have to find the algebra slope. And then we're going to find out when they are equal to each other. And just ensure that when that happens, it's inside of this interval. All right, go. For me, the algebra slope is the easiest thing to do. The problem here is I have my x values, but I don't have my y values. So I have to find the y values, the average rate of change. I jumped way ahead, sorry. Make sure you state the conditions. F of x is continuous over 3 to 6. Because when isn't it continuous? What value for x will make this not continuous? 0. So x equals 0, then we have a problem. So that's fine. And it's differentiable over that as well. There's no sharp turns or anything like that. Most of the time you just state that. You don't really have to say why. Okay. Let's go average rate of change. In other words, algebra slope. Okay, so I need 3. And so I plug 3 in, and I get 3 minus 2, which is 1. Then I plug 6 in, and I get 3 minus 1, which is 2. So now I have my points. 3, 1, 6, 2. Slope from 2.3 of the Algebra 2 book is 1/3. Okay? So when I connect the points on the graph where x equals 3 and x equals 6, I get the secant line, and the slope of the secant line is 1/3. So somewhere, maybe multiple times, along this curve, there's a tangent line with this slope. The mean value theorem guarantees that. So I need to take the first derivative of that, instantaneous rate of change. So I take the first derivative of that, and so I just went ahead and rewrote this as x to the negative 1. First derivative at c, we don't know what the c is, somewhere. Okay. The 3 drops out, this becomes positive 6, x to the negative 2, then I insert c in for x. So somewhere, to find c, this has to equal this. And so from here, it's just a matter of solving that. And I went ahead and changed this to make it easier to do. 6 over c squared, that has to equal 1/3, which means c squared has to equal 18. So c has to be the plus or minus square root of 18. Now I put both, because whenever you take the square root of both sides, you always do plus or minus. And then we have to determine if it's in the interval. Of course, the negative can't be in the interval, so we know we can throw negative square root of 18 out. I don't know what the square root of 18 is, but I do know that it's definitely in between what two whole numbers? What two whole numbers does the square root of 18 have to be between?
16 and 4 and 5. All right.
The square root of those.
4 and 5.
Yeah, so 4 and 5. The square root of 16 and the square root of 25. So this has to be between 4 and 5, which is in the interval, right? Between 4 and 5. I don't actually even need to know what it is. Okay. It has to be in the interval, and so that's why negative 1 out. And so c is the square root of 18. So at the x value, square root of 18, whatever that is, 4 point something, there's a guarantee that the slope of the tangent line will equal the slope of the secant line. And that's a huge idea in calculus. Okay? It's kind of cool.